Good afternoon once again, and good evening to those of you in Europe, and good morning to those of you in Australia and places far away. Welcome to session 10 of the ESIG 2021 Spring Technical Workshop. We have another great session lined up for today, looking at what's going on in the wonderful world of hybrid power plants. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As you know, our spring workshop sessions are all being held online and are open to everyone. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoivasan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who really make ESIG what it is, and we encourage you to become involved if you're not already. Regarding logistics, I would ask you to note that the webinar will be 90 minutes long. We had a lot of feedback that our 1-hour workshop sessions were too rushed, so we're experimenting with some longer formats for the spring workshop. Our revised format today will have 3 individual presentations of approximately 15 to 20 minutes each in the first hour, followed by 20 to 30 minutes of Q&A after the last speaker. As we are doing with all our webinars now, we'll be using the Slido platform for managing the Q&A, not the WebEx platform. You should go to slido.com on your device and enter ESIG1 as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also in the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we will address them at the end. We will follow up with written answers to any questions we don't get to during the Q&A. Recognizing the limitations of a webinar with more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG1 as the event code. Today's session is titled The Evolving Hybrid Power Plant. This is one of the most quickly changing parts of the energy landscape today. The rate at which the technology applications are evolving is simply amazing. Today's session will build on the sessions from our previous workshops and ongoing industry developments. Looking at a future where most of our generation could be coming from hybrid variable renewable power plants in an environment characterized by variability and uncertainty, this is clearly another important topic. The session will be chaired by Derek Stenclik, a co-founder of Telos Energy. Derek has a long history in system planning, operations, and reliability, and is a strong supporter of our system planning activities here at ESIG. Derek is a familiar face at ESIG and is well known to many of you. He's a good friend, and we look forward to his continued participation. We're very happy to have him here with us today. Derek, thank you for chairing the session, and I'll now turn it over to you.
Thank you very much, Charlie, and thank you everyone else for joining. I'm really looking forward to this panel session today. My name is Derek Stenslich, and the founding partner of Telos Energy. And again, very excited to introduce not only this topic, but what we have in store for you, a great set of panel experts to speak through their thoughts, their latest thinking when it comes to hybrid power plants. And when it comes to hybrids, I have to admit, I'm a recovering hybrid skeptic. I spent the first half of my career fighting tooth and nail, saying you don't need to add batteries to wind and solar plants just to manage the variability. There's better ways to do that. There's more economic ways. And of course, at that time, battery storage was expensive. And I still stand by the original statement. We don't need storage just to manage the variability. But what I didn't see coming is a huge shift, not only in the cost of batteries, but just in the way we think about what a power plant is and what a wind plant is or what a solar plant is, and really looking at ways that we can combine resources and extract value, not only just adding cost or capability, but add value not only to the developer, but to the system and ultimately to the ratepayer. So a lot of stuff has happened between then and now. Obviously battery costs dropped dramatically. But other things happened as well. So solar panel costs dropped too quite a bit in that time period. And what you saw developers do is they kept increasing the amount of panels they were putting behind a point of interconnect. So the higher inverter loading ratios became the norm. I won't even begin to quote what some of the latest coming out. I think we have some panel experts that will talk through that. The ITC, the investment tax credit, was extended not only to the solar plant and the renewable generation, but also to everything kind of behind the fence. And so batteries fell in and we're able to capture some of those tax credits. Grid services are continuing to evolve. So there's now developers and plant owners are not just getting paid for the energy they're producing, but all of the grid services they're also able to produce. So that's opening up new revenue streams for these plants as well. And really, there's just inherently a different understanding of risk. These are 20, 25, even 30-year assets that we're seeing with solar and wind plants going in. And so with a market that's becoming more and more volatile, storage allows developers and plant owners to have a hedge against that future market uncertainty. I spend a lot of my time walking through different scenarios of what the grid might look like 10 or 20 years from now. And what I can tell you is they're all wrong. And we don't have a clear answer a year from now, let alone 10 years. And so while it's useful to go through those exercises and to understand what the future could look like, having a tool like battery storage in your toolkit to help manage that uncertainty can be really valuable. And I think we have some good comments from the panel today to talk about that. And just really, we've made a shift in my view for the industry. We're not just talking about adding renewable energy, but really replacing fossil altogether. And that means not only the energy those plants are providing, but the capacity and the grid services as well. And again, hybrid resources allow for that as well. And frankly, we just got a lot smarter. Where I was 5 or 10 years ago thinking about how to integrate batteries onto the system is nowhere near where we are as an industry today. So I've learned quite a bit. I think the industry as well has learned quite a bit. So I'll say I'm a recovering skeptic, but also very much an optimist in this space. And I really do believe we've only scratched the surface on where hybrids are going to take us. And I'm really excited about the technology. I'm excited about the market interactions, and I'm excited to see all the ingenuity that hybrids are going to bring to the industry. And I think a lot of the folks listening to the panel today are going to be the folks that bring that ingenuity. And I think hybrids allow for that optionality and the ability to bring new ways of thinking to the power industry. So with that, I'm going to hand it over to the panel. I'll give you a brief intro now and then a little bit more extensive one before I kick off each speaker. So we're going to start with Andrew Mills from Lawrence Berkeley National Lab, then pass it over to Mark Rothleder of California ISO. And we're going to wrap it up by leaving California and send it over to Mark Ahlstrom from NextEra and the president of ESIG. And then after we give the three of those folks a chance to speak, we're going to open up to a panel discussion where we can go a little bit more free form on the topic and also answer all of your questions. So please start thinking of questions, submit them to the Slido portal, and we will get to that shortly. And so now it's my pleasure to introduce Andrew Mills. Andrew is a research scientist in the Electricity Markets and Policy Group at Lawrence Berkeley National Laboratory. Andrew's research on the integration of variable generation into the electric power system focuses on cost, benefits, and needs for supporting infrastructure. Andrew has a PhD in energy and resources from UC Berkeley and a bachelor's in mechanical engineering from the Illinois Institute of Technology. So with that, I will pass it over to you, Andrew. Take it away.
All right. Thank you for the introduction, and thanks for the opportunity to share results from some of our research on enhancing the value of solar at higher solar penetration levels. This particular project was led by James Kim with contributions from a broad team of researchers at the Berkeley Lab and was funded by the DOE Solar Energy Technologies Office. We're seeing the marginal market value of additional solar decline with increasing penetration levels in the California ISO. The impacts of solar on the CAISO system are relatively easy to spot. We see changes in the net load patterns. We see similar shaped changes in the wholesale market prices for energy in the real-time market. We see increases in the regulation down prices in solar hours in the spring. In idealized competitive wholesale markets, these market prices reflect the marginal cost of meeting demand at each moment. And the revenue earned from selling power to the market informs the system value of solar. And even in realistic markets, the prices and revenue from selling power at the prevailing wholesale price inform the merchant revenue of a plant or the opportunity cost for a purchaser getting power from a solar plant rather than buying power at the prevailing market price. Either way, our interest is in looking for ways to mitigate this observed decline in the market value. There's ways to do that at the system level, such as by making the system more flexible with initiatives like the energy imbalance market. But there's also ways to boost the value that are within the control of individual plant developers or purchasers. So in this research, we sweep over a wide range of options using a consistent economic framework to compare the attractiveness of various options relative to a base PV plant that's just a standalone south-facing fixed tilt plant. Now, some of these options are fairly straightforward. We can add tracking or we can orient modules towards the west. And then some of them are a bit more exotic, such as taking a bifacial panel and orienting it vertically on a north-south axis so that the production is shifted to mornings and evenings. And we can also look at adding storage to the base plant or to any of these other configurations. In total, we looked at around 10 different options for increasing the value of PV, all of which, again, are largely in control of the plant developer or the owner. And for all of these options, we used a consistent decision framework. We first asked how the option increases the market value relative to the value of that base PV plant, and that's shown by the vertical axis here. We then asked how that option impacts the levelized cost relative to that base PV plant, as shown on the horizontal axis. If the option increases the market value by more than it increases the cost, then overall the option is more economically attractive than that base PV plant, and you end up in the region shown by this blue triangle. That's our target region. On the other hand, if it increases the market value, but not as much as it increases the cost, then you can end up in this red triangle, and you might have been better off with just the base PV plant. It's important to note that we're calculating this market value of the grid-free PV-friendly option relative to the base plant under the same market conditions. So in other words, we first look at the value of this grid-friendly option relative to the base plant at low solar penetration levels. And separately, we're going to go to look at the value of that grid-friendly PV at high solar penetrations and the value of that base PV plant also at high solar penetration. I've included this slide here that shows some of the key assumptions and methods for the calculations, but mostly just as a reference. I'll just note a few highlights here. So first off, our base PV plant is a fixed tilt south-facing plant that's sited near existing plants in the California ISO. We compare this one to a wide range of options using the framework shown on the previous slides. And we'll show the results of this comparison at less than 2% solar penetration, where we used wholesale power prices from 2012, and with more than 16% solar penetration using wholesale power prices from 2018. And in this case, we're using historical prices from the SP15 hub in Southern California. We estimate this marginal system value by calculating the wholesale market revenue with real-time electricity prices. In addition, we're going to allocate a capacity price adder to each of the top 100 net load hours. And we use this approach since the historical capacity credits available from the Public Utilities Commission are for a generic solar resource and don't account for differences in the timing of production. Our capacity price adder approach is a simplification, but it's responsive to the shifting timing of the peak net load with growing solar. Then all of our cost estimates will be reduced by this federal investment tax credit that Derek mentioned earlier, both for solar and for the storage. And when we calculate the impact of adding storage, we always size the battery to 50% of the nameplate capacity, and then use a 4-hour duration storage that's AC coupled, except where noted. And we're also going to assume that the interconnection size is always based on the solar nameplate capacity, and that the storage can only charge from solar. And then we're going to dispatch that hybrid using two different approaches. Our upper bound or more optimistic case assumes perfect foresight of prices and dispatches against those, whereas our lower bound or pessimistic case uses an implementable but naive strategy where the dispatch is based off of a day-ahead price and a persistence forecast of solar, and then the resulting revenue is based on what the actual real-time price was. And an important note on the hybrid value is that we're valuing it using the simple self-scheduled approach where it can earn both capacity and energy revenues. This doesn't include the potential for hybrids to access other ancillary services, nor does it capture some of the more difficult to monetize factors that are not really reflected in these historical market prices. So with those caveats and that overview, let's move into some of the results. One of the things we find is that many of the grid-friendly PV options do increase the value relative to the value of that base PV plant, both at low solar penetration and higher solar penetration. And we see that many of them achieve this increase in value by shifting their production towards the higher price periods. The highest increase in value comes from adding storage to the base PV plant, as noted by these hybrid markers. Now, whether these options are actually improvements over the base PV plant also requires that we consider the impacts to the cost relative to the cost of that base PV plant. As a reminder, if the value increases more than the cost increase, then the option will show up above this dashed line and will be in our target region. That's what we're looking for. So with this in mind, adding tracking is clearly advantageous. It increases the value both at low and high solar penetration by having more of its production aligned with high prices. And at the same time, it also has a lower levelized cost of energy. A number of other options can similarly provide net benefits, but we see that some of them are more marginal. So the west-facing panels, for example, they produce net benefits at lower penetration, though it doesn't increase in value by as much at the higher solar penetration levels. And this more exotic vertical bifacial is just marginally more attractive at high solar penetrations. And for both of those options, the west-facing and vertical bifacial, they achieve this higher value at the expense of somewhat lower production. And hence we see this shift in the levelized cost to the right. So that lower production leads to an increase in levelized cost. We also looked at the ability to provide regulating reserves, where we saw that we could increase the value by a few dollars a megawatt hour, again, just from the base PV plant. And then we could change the location of the plant. We can go from where existing plants are in Southern California to other nodes across California. You can see that some of them do increase value and lead to some net value gains, though most of them are not as attractive as what we see in the desert in California. So the impact of value that we see at high penetration depends on the way that production is shifted by the different options. Here we show how the seasonal average diurnal production profile of the different options, along with the price patterns, inclusive of that capacity price adder. The increase in value comes primarily from shifting the production towards the late afternoon and into the early evening. But by the time you get to high penetration levels, that peak is shifted almost all the way out of the window for solar production, except for that hybrid plant. This chart also explains why the west-facing did better at low penetration. The west-facing here is in this light blue line. And you can see that at low penetration, it's really well lined up with the high price periods at low penetration. But it has a hard time keeping up with that shifted peak at higher solar penetration levels. So that was with our base plant. Now let's ask a slightly different question, where we're going to start to add storage to all of these different options, not just to the base PV plant. So now all of these are looking at hybrid cases here. And what we see is that the storage behaves in quite similar ways, no matter what that underlying PV subsystem looks like. The storage is always able to shift the power into these high price periods, and it does that more effectively than these standalone options did. So that means that these hybrids will tend to have similar value irrespective of what the underlying PV system looks like. And in fact, shifting the power around with the PV subsystem becomes somewhat redundant with this energy shifting capability of storage. So even though what we see is that the hybrids have somewhat similar values, the additional costs of storage end up being allocated over widely varying annual production levels, and that impacts these levelized dollar per megawatt hour costs. So this is illustrated with our framework by showing that the range of market value across the hybrids, which is the vertical side of these rectangles, is somewhat smaller than the range in the levelized cost across these hybrids, shown by the horizontal side of these rectangles. What ends up happening is that the most attractive hybrids are those that maximize the energy production and end up with the smallest increase in costs relative to that base PV plant. In fact, the one that jumps out the most is a hybrid plant that combines the tracking with high inverter loading ratio and is DC coupled to capture that clipped energy. So this next slide just takes that same data and presents it in a slightly different way, where we're now just emphasizing how much more attractive these options are relative to that base PV plant. And again, we see that these generation maximizing strategies with the energy shifting capabilities of hybrids result in the highest net value at higher solar penetration. And here, all of those hybrids are shown in the blue markers, and the upper bound estimate, assuming perfect foresight of prices, is shown with the upward pointing triangles, and that lower bound estimate from our implementable day-ahead scheduling algorithm is shown by the downward pointing triangles. and then the standalone options are marked by the circles. If you're looking at low solar penetrations, shown by the open markers here, that standalone west-facing PV system could be almost as attractive as the lower bound of that DC-coupled hybrid with tracking. But by the time you've gone to high penetrations, which is shown by the filled-in markers, the hybrid options all become much more attractive than they were at low solar penetration. While that west-facing panel, in the standalone case, it was somewhat less attractive than they were at lower solar penetration levels. So if you were to then go and couple storage with that west-facing system, you'd end up with this high cost from the low production that would result in it being much worse than that base standalone south-facing PV system. And instead, what you want to do is focus on these ones that maximize the overall solar production and spread that cost over a larger amount of megawatt hours. So in conclusion, we find that there are some ways that you can modify the standalone PV systems to increase their net value, though what we saw was that these net value gains for standalone PV were somewhat modest. Adding storage, on the other hand, can alter the cost and value dramatically. And the strategies that involve shifting the timing of generation at the expense of lowering overall PV production ended up resulting in net value penalties once storage was added to the cost. And part of this comes because that temporal shift becomes redundant with the energy shifting capabilities of storage. So instead, what we see is that the strategies that maximize PV production, those provide the largest net value gains when combined with storage, especially at the higher PV penetration levels. So finally, I just want to note a few other ongoing projects related to hybrids within the Berkeley lab. And most of this is supported now primarily by the DOE Strategic Analysis Group. So Will Gorman in our group is finishing up a paper on how the value of these coupled wind and solar hybrid systems vary by location across the United States. Chris Crespo is working on a more systematic sweep across all these different configurations, including going to even higher inverter loading ratios, increasing the duration of storage, and changing the sizing of the storage relative to the plant capacity. And then Fritz Karl and James Kim are looking at the ancillary service value of standalone and hybrids in a lot greater detail. And we're about to kick off a project with EPRI that will examine the economic and reliability implications of different wholesale market participation models. And beyond this Berkeley lab work, our colleagues at NREL are looking at hybrid configurations using future prices or incorporating hybrids into capacity expansion models, and then looking at opportunities for wind and solar hybrids around the country. We look forward to discussing this research with you all in the future.
All right, thank you very much, Andrew. Appreciate that perspective. And again, that's really the ingenuity that I think I spoke to when I first kicked off this session. I think there's a huge opportunity for researchers and folks like Andrew to really, now that we have such a flexible tool, to just really think of novel ways, new ways to find value out there in the market. So with that, it's a good transition when we talk about markets like Andrew just did, to pass it over to Mark Rothleder. Mark is the Senior Vice President and Chief Operating Officer of California ISO. Mark's been with the ISO for 24 years, where he has utilized his power engineering experience to develop operational and market solutions for California and the West. So I think he adds a great perspective of the grid operator and how markets need to transition with these types of new resources on the system. So with that, I will pass it over to you, Mark. Take it away.
Great. Thank you very much. And thank you for the opportunity to discuss this very timely topic. Before I do that, I want to just acknowledge Andrew mentioned the energy imbalance market as one of the solutions for navigating the transition. And I want to acknowledge that this morning we onboarded 2 additional EIM entities, the LA Department of Water and Power and Public Service in New Mexico. This is in addition to last week, Turlock Irrigation District and the balancing area in Northern California, Phase 2, with some additional load serving entities in that balancing area. And I think this is just a great accomplishment, but it also acknowledges that the system is changing across the West, and solutions and the being able to diversify the mix of resources across the West becomes an important tool going forward. what I'm going to start with today, though, is just to acknowledge, as we did probably several years ago, some of the operational challenges as we navigate the grid transformation. And I'll just focus on 3 areas, including the challenges of meeting the later summer evening peak load, increasing ramping needs, and multi-day weather events. And I focus on these because these are all areas where I think storage, and more specifically hybrid resources, have an opportunity to help meet these challenges. So if I look at the first one, the challenging of meeting the evening peak, this is really as a result and something we started to observe and actually lived last summer. And that is, as we get increasing amounts of penetration of grid solar and behind the meter solar, what we're seeing is that the peak, or the level of the peak, is continuing to extend out, and actually it's flattening, so that while your peak may be something around 4 p.m., the level of the load, because the solar production behind the meters decreasing, the load is coming back to the system. We're seeing that high loads continuing to increase into the evening hours. And in fact, as that occurs, what we see is high loads occurring, and the effectiveness of solar production is decreasing. And that's, if you measure the effective load carrying capability, we see a decrease of the effective load carrying capability of the solar resources. And you couple that with the fact that we are decreasing our reliance on gas resources, including retiring of once through cooled resources. And what we started to observe is that especially around 6 to 7 p.m., as the sun goes down and the loads are still high, we are started to observe potential for capacity shortfalls during this time. And in fact, that is kind of what occurred in the August timeframe of last year with the West White Heat event. It was that time that became the most critical time as the sun went down and the loads remained high. Fortunately, the California Public Utility Commission had already set in motion movement towards getting additional capacity. And it's this year that this additional capacity, in the form of about 1,500 megawatts of additional storage, is starting to come onto the system. And I will highlight that the ISO supported these in terms of an interconnection process by evaluating, since those solar resources were decreasing in their capacity during these periods of time, we recognized that we could actually make use of the deliverability space that existed at those locations. And we did a special evaluation in 2020 to evaluate where there's opportunities and see if there was modifications to accommodate and quicker, timely storage resources added to or co-located or in hybrid situations with solar resources. And in fact, we had about 10,000 megawatts of interest in that special evaluation process. The next challenge is basically this continued increase with the solar resources. We're seeing our net load continuing to decrease. And in fact, we're now at points where our net load on a 50,000 megawatt system, peak system, we're seeing net loads approaching just under 4,000, around 3,500 megawatts. And we're going to get to the point where the net load will actually drop below zero. The consequence of the net load dropping is that in that evening, as that evening comes and the solar production goes down, we're seeing increasing amounts of needing for ramping capability in that evening period. And what used to be about 15,000 megawatts of 3-hour ramp capability needed in 2019, we're predicting that by 2030 we could be as much as 25,000 megawatts over a 3-hour period. that is quite a lot of ramping capability, and the question is what could help navigate that. And you need probably something like a 3 to 4 hour storage resource or other resources in large scale to help navigate that change. And the opportunity here is that you can charge in the middle of the day with that surplus solar production. The last one challenge is something that is probably still emerging and not right in front of us, but we do see at times in the winter or in the springtime period whereby we have multiple days of cloud cover, and during that time the solar production is roughly running around 15 to 20% of the capability over multiple days. And the challenge there is that if you have multiple days of that low solar capability, you're not going to be able to have the surplus energy on a daily basis to charge those batteries. And so you have to start looking for other solutions or charge when there is a surplus on other days. Just contrasting this is on the left-hand side is a typical solar day, a clear day, where you have lots of solar production. On the right, you see where you have low solar production for multiple days, and then you're seeing how, in fact, you're currently using gas resources and imports to make up for that difference. And this is another opportunity where if we can store that and use that storage capability to navigate multiple days, that's another opportunity. I already mentioned something about the interconnection process. We're seeing, at a general level, we're seeing increases in our queue of storage resources and co-located resources, and in large scale. And usually when we see this in the interconnection queue process, it's an indicator that there is sufficient projects to choose from if there is a demand for that capability. And on this graph, you can see here that we are now in the queue in the June 2020 period, we're seeing well over 70 gigawatts of storage in the queue, and roughly over 50% of that in the queue is actually hybrid resources, where they're co-located with either solar or wind resources. The rest of them are either standalone or otherwise. So at a high level, we're seeing the hybrids co-located resources significantly increase. As I mentioned, we're going to have about 1,500 megawatts of additional resources. Many of them are co-located in hybrid situations. Why is that occurring? One, as Andrew indicated earlier, the increasing value at the high penetration of solar, adding that storage provides value. It extends and smooths the production of the variable resources. So where in the middle of the day, you've got that surplus energy, extending that out for that production capability over 4 hours allows us to navigate that operational time frame that is difficult in the evening hours. It makes logical sense because it becomes an efficient use of existing land, because if you co-locate it where there's already existing renewables and there's some extra space, or you plan it that way, it's a good use of the plan and also transmission assets, and including the efficient use of interconnection capability. Lastly, it's an efficient source of charging the energy. So we talk about hybrid, but really in the ISO, we're actually set up policy for recognizing two methods of hybridization. The first one is really a hybrid resource, whereby the two components or multiple components of the variable resources and the battery are actually acting as one resource, one hybrid resource, and we actually treat that as one generating unit from a dispatch and forecasting perspective. The advantage from a resource adequacy perspective, and this is evolving, is what is the value and what is the resource adequacy value of the qualifying capacity of those resources. Certainly the limitation is the limitation of the interconnection, but up to the interconnection limit, we moved from a maximum of the two components to an additive approach, whereby the added addition of the effective load carrying capability with some discount for the amount of charging energy that would be used to charge the batteries, plus the effectively the nameplate or the Pmax capability of the 4-hour sustainable production of the battery. In contrast, on the co-located scenario, we treat these two resources as independent and separate resources, not as a singular resource. And we can dispatch the resources, the variable resource and the battery resource independent of each other. But we can also optimize by applying the point of interconnection constraint. We can optimize those resources behind that constraint so that we can charge the battery when we have the surplus or additional energy from the variable resource. Again, even though when you treat these as separate resources, each component will have its own qualifying capacity as a resource adequacy resource. The variable resource will be effective load carrying capability, again, discounted by the charging energy, but the battery itself will have its own separate qualifying capacity as a 4-hour sustainable production of the battery. Again, in the co-located approach, we actually treat these as separate resources, and we do a forecast, and we can dispatch these resources separately and provide effectively other services as independent resources. So in closure, I just want to summarize looking forward the additional opportunities and considerations of these hybrid resources. We are getting to scale now where we are learning about these resources, but these hybrid resources, unlike variable resources as a general matter, these hybrid resources, I think, provide a better opportunity to provide ancillary services at more like a traditional conventional resource. And we look forward to the opportunity of getting these ancillary services. We will have to manage the interconnection constraint in a different way so that we can manage both energy and ancillary services to ensure that those ancillary services behind the interconnection are deliverable. We do have to consider the investment tax credit effect of charging the storage. While there are times where we may want to charge these batteries from the grid, the investment tax credits put some constraint around that, because in order to get the investment tax credit, you have to maximize the amount of charging from the variable resource that's co-located behind it. And that kind of leads to the opportunities and benefits of the potential DC to DC charging, that you can avoid the losses across the inverter. Lastly, we talk a lot about the grid opportunity for these hybrid resources, but there's also increasing opportunity, and we're seeing the distributed energy resources set up hybrid scenarios as well, either as hybrids or in microgrid situations. As we consider those resources, it also opens up the need to consider matters around distribution interconnection, and how do we ensure that if those co-located or hybrid resources are sending energy back up through the distribution of the system, that they're doing so in a secure and planned way. Similar to the grid connected resources, how do we account and properly account for the resource adequacy capacity of these distributed energy resources? And lastly, there's work to be done to ensure that we do proper measurement and verification, knowing that some of these behind the meter resources may be actually providing net energy metering, and how do we ensure that the value of the incremental capacity that's being provided to the grid is being compensated. So with that, I look forward to the rest of the conversation and discussion in this panel. Thank you.
Thank you, Mark, and really appreciate your perspective coming from one of the grid operators, and probably the grid operator seeing the most activity in this space. And I think what you showed with that interconnection queue, there's a tidal wave of new projects coming your way. So really appreciate the hard work you and your team are doing to facilitate that. So we just got two perspectives really on where hybrids are today and why we're seeing some of these changes. We're going to mix it up now and pass it over to Mark Ahlstrom to really look at a future look on where hybrids could go. And so Mark Ahlstrom is obviously a household name when it comes to this ESIG community, although you may not recognize him today. Mark is the VP of Renewable Energy Policy for NextEra Energy Resources and NextEra Analytics. He serves on NERC's Reliability Issues Steering Committee and has worked for almost 2 decades on the reliable integration of variable generation into power systems and markets. Earlier than that, he was the founder of 2 software companies. And as you all know him here, he's also the president of the board of directors for ESIG. So with that, I will hand it over to Mark.
Thank you very much, Derek. Yes, I still have the ponytail. It's just no longer attached to my head. It's in the bottom of a drawer. So a little change in look here. As Derek mentioned, I think all of us started out as skeptics around this concept of hybrids. You know, we were saying that there's just not that much need or value to use storage to firm up a variable resource. And I think we were still right. What we didn't realize was that there's a lot more going on here than just firming up the variability. And in fact, you're creating a whole new generation of software controllable resources that is extremely exciting. But the pace of this has been just truly phenomenal. You know, at least maybe there's some of you participating here that have been thinking about this in this way longer. But you know, I'd say that the change in thought about this really has happened mostly over the last 2 years, right? When we started looking at what this really means and started a lot of these discussions. And a lot of those did take place, I would say, at ESIG and related activities. So this is an exciting time. These hybrids are real. Actually, these are projects that were built as, you know, became hybrids anyway, going on 3 years ago now. So they've been building them for a while. These are examples of 2 projects down in Florida in the FPL service territory. The one on the left, Babcock Ranch, is an AC coupled. You can see in this case, the way it looks is that the batteries have of course, their own inverters. So they're usually located near the substation and they connect at the AC connection point in the substation itself. Now there can still be a plant controller there, of course, that's going to coordinate the PV and the storage, but it's more at that substation level. On the right is the Citrus Energy Center. This was actually built, ironically, as a PV-only plant, and then it was actually retrofitted a couple of years later to add storage. And it's a DC-coupled design. As you see, with all PV plants, typically anyway, there's an inverter that's actually out with each of the inverter strings. So the AC inverters always tend to be distributed throughout the PV plant for a large plant. And with the DC design, since you want to share that inverter, you would typically put the storage next to the inverter out there in a more distributed fashion throughout the site. And often there's a DC converter because the optimal battery voltage that it likes is different typically than the PV voltage. So if you're going to use the PV inverters, there's often a DC to DC converter, which is kind of like an inverter itself in a way, but just does a voltage change. So these have been around for a couple of years. They're real, they exist, major projects, and they're working very well, both AC and DC coupled. Now this concept of, you know, AC and DC coupled, though, I think is often misunderstood. Here's some one-line diagrams of the 2 of them, right? AC coupled, solar and battery have their separate inverters. DC coupled, they share the inverter, but there's often a DC converter. But people think that, well, the AC coupled is co-located because they're separate resources, and the DC coupled is hybrid as a single resource. And I would actually encourage you to say, no, that's not true at all. These are all software devices. We can make either one look hybrid or co-located, regardless of whether it's AC or DC coupled. It's software. We can make it look like we want, right? Similarly, you know, Andrew showed the example of going to a higher inverter loading ratio where we add more solar panels. And he was assuming that was going to be a DC couple because we had used that to charge the battery. Well, I can do that on an AC couple too. The difference is I have to oversize the PV inverter. But once I do that, then I could, for example, if that's a 100 megawatt plant where it injects into the grid, I could have 150 megawatts of solar generation at some instant. and I could be, have 150 megawatts of solar. I'm using 100 to go out to the grid, and I'm using 50 to charge the battery. So on that, I'm still just injecting the maximum 100 megawatt injection limit. So you could actually do it either way. It's purely an internal optimization. What's the cost of these inverters versus the DC converters and so forth, and what are the losses and all that. But that will all change with future equipment. So I encourage you to keep this separate and to leave that up to the designers of the plant to determine the optimization at that point in time with the equipment that's available. So to clarify the definitions of this too, and I agree with Mark's general definitions here that are very consistent with the ones I've used. The hybrid is the single resource that is really controlled behind that point of interconnection by the owner-operator of the hybrid plant. It presents to the market and to the system as a very simple, fairly generic sort of generator interface or some higher level services interface in terms of all the ancillary grid services it can provide. But it's actually quite simple from the point of view of using it, of course, from the system operator. Now, if you treat those as multiple separate technologies, then it's co-located. And I understand why a lot of people are doing co-located, because it's kind of a smaller intellectual jump from the standalone resources we're used to. I am not shy about hiding my, let's say, disdain for that. I think that in the long run, the hybrid as a single resource will prove to be much more useful. And we'll talk about why, but it comes to a lot of that innovation and hedge value that Derek alluded to as well. I also think that the hybrid approach is very similar to what we're trying to do in the future with other things like aggregated DERs, virtual power plants, DSOs, distribution system operators. All of those could conceivably be the same sort of participation model as a hybrid. So I understand why we're going to do a lot of co-located, and we're doing them as well at NextEra, for a lot of different reasons, but I think the hybrid is the one to watch. In fact, I go further. I spent 20 years in the software industry before I accidentally ended up in energy. So I think about things like parameterized function calls and object-oriented programming, right? And that's a great way the software industry started dealing with complexity going back to the 70s and 80s. And really, I look at this hybrid as a single resource, as an intelligent agent, where you're leaving it up to that agent behind the services interface to deal with what's the best way of providing those services. And when you do that, you leave them open to being very creative to innovate and update and reprogram behind that interface to keep figuring out ways of doing it better. In fact, fundamentally, these are all software devices. And now you give me enough energy, storage, electronics, and software, we can make that look like any kind of electrical machine you want at that point of interconnection. And I'm taking the argument a step further and says, focus on that point of interconnection, the services you want there. How we do that inside the plant is not your problem. That's our problem. And we want to be able to continue to innovate and improve on that over time. Okay. This was alluded to as well in terms of what Andrew was talking about with the DC coupled design with the higher inverter loading ratio, or I call it here the DC-AC ratio. If you do an optimized standalone PV plant today, which is shown as the lighter green there in the bottom, it optimizes out, so a 100 megawatt PV plant would typically have about 130 megawatts of PV panels to make up for losses and less than sunny days and so forth. And you're going to have a certain amount of energy up there that's clipped that you can't deliver to the grid, that's kind of thrown away. And so what happens now, because if you are adding additional solar back there, say up to 1.7 or 1.8 I'm showing here, then you end up with not only wider shoulders, which makes it a better standalone solar plant in a sense, there's more energy there, but you then get that additional peak, right? Now that's a lot of clipped energy, in a sense beyond that 100 megawatt limit that I can put in the grid at any instant. I might have 180 megawatts of solar generation at some instant. But if I have the battery, I can use that to charge the battery and shift that to other services or shift the energy to later in the day, as Mark was talking about. As I pointed out, I think you can actually do that with either a DC or an AC coupled design. The DC coupled design is probably penciling out to be the way to do it today, but not necessarily the only way you could do it. But I also think this is leading us to think about a lot of other things that are going to happen a lot sooner than we think. Yeah, we can add more generation. We're already doing that, but I can add other types of generation. And I can add it either in a DC or AC connected configuration inside the plant, right? Maybe I add some other clean, cheap energy. Maybe it's inflexible. I don't care. I've got the battery. I can make it look flexible. What about long-term storage that Mark was alluded to? Absolutely. We're going to come up with new ways of having longer duration storage. A lot of that might be less flexible or have startup times or things like that. That's great. So do I want to connect that separately as an independent resource to the market and the grid? Or do I want to put it behind, as an integrated part inside this intelligent object? And then I can make it look like anything I want as well. So if I'm going to start putting in longer duration storage or hydrogen electrolyzers with a fuel cell as a form of long-term storage, I think a lot of that is going to actually happen first inside hybrids, where we can optimize it as a subsystem and present it to the market and the system in a very simple services level interface. It's largely transparent to them, but now I've got additional capacity. I've got additional capabilities. I have longer duration. It's magically just done by changing my offers. It's not done in how I have to change my registration or even in many cases, you're not even changing the electrical properties if you're using the same inverters. So you can do that without, should be able to do that without a material change or other changes in the electrical properties or the dynamics of the system. Not only that, but I think we're going to start seeing ourselves wanting to add a lot of loads behind the hybrids as well. Electrolyzers, data centers, other types of loads. Yeah, it starts looking like a large transmission connected microgrid or a DSO or something else. And I think that's great. If it has a simpler presentation to the system and it provides more services and capabilities to everybody, what's wrong with that? So the key benefits are, we can start out emulating any kind of resource model you can give us. It might not be perfect, but I can start by looking like a renewable plant that doesn't have to retain headroom anymore to do ancillary services. Or I can look like a gas plant, but I can start instantly and ramp all the way to zero. There's probably some more ideal participation model that's just a really generic generator model, but we'll get there eventually. There's batteries in here. Batteries are kind of complicated. They're not really a generator or a load. There's got a whole bunch of these parameters under 841. I can hide all that inside a hybrid and still give you all the same services, right? So I think it's a more flexible way of dealing with that and the battery innovations that we're going to have as well. And it also, of course, it gives you a very simple market resource that makes one part offers, meaning there is no startup cost or min-gen. So you can actually even talk about market simplifications. I mean, theoretically, of course, any generator could become a hybrid and could go to one part offers. Just don't allow anybody to have a forward commitment that we're going to start them ahead of time or give them allow them to have a minimum generation limit or pay uplifts and so forth. You could force them to do that. We're not going to probably do that with all the conventional resources, but as we get to more and more of the system actually being these sort of digitally controlled, mostly hybrid resources, why not simplify the market as well? But still, a lot of people come to me and questions about, okay, well, what is it? Is it a microgrid? Is it starting to be a DSO? Is it an object? It's all these things. And the key characteristic to me is nothing really about energy shifting or co-location. It's the services level. It's that I can have some sort of, what do you call it, an aggregated resource or some other term. It's putting this behind a services level so that you can continue to innovate and evolve behind that interface. Another question I get is earlier, going back 3-4 years ago, when we were talking about 841, I was talking about something called the universal participation model, which was really just similar to what came out with Order 841 for storage. It was saying that I don't want to have to create a new market participation model for every new technology that comes along, right? So can't I just have a parameterized market participation model that would allow me to essentially, just change parameters so that anything could immediately participate in the market? And 841 kind of took that approach, right? There's this whole page of additional parameters. The hybrid model that I'm proposing here is completely different. It says, no, you don't parameterize the market model at all. You instead have this higher level of services. You simplify the market model. You probably create additional grid services or ancillary services to provide other services like flexibility, things like that. But you simplify it and you expect the resource to emulate that interface, not pass the parameters over to the RTO and expect them to optimize it for you. I mean, fundamentally, this is getting away from that sort of top-down, I'll just be the investor in this generator. Here you go. You're the system operator. You optimize my operation, my revenue for me, rather. I'm saying that should be the responsibility of the market participant, of the hybrid owner, and that we should try to make things simpler in the real-time control room and in the market software rather than make it more complicated. So in a sense, I'm obviously being a bit critical of 841 as well, because it kind of took this universal participation model version 1 approach. Turns out it's not all that general. My big complaint with it is that it's treating storage as only storage. It treats it mostly as a price arbitrage resource, just an energy shifting. I think that's short-sighted. Storage is much more than that. We've seen what's happened with all other industries once they integrated storage, and it turned out to change all kinds of things. Why do we think it's just going to be a simple shifting resource? I think it's going to be much more than that. And also, I'm just wrapping up drafting a paper with a bunch of brilliant folks that are more from the economics and the storage and the how do things become cheap sort of approach. Some of the authors you may know here. And we said, are there these other longer term benefits? In the near term, yeah, we're responding to, the ITC makes storage cheaper, so we take that. We have a lot of interconnection delays and costs in a lot of the other RTOs. Not California is doing well, but some of the others there, it takes years to get a new resource through the interconnection queue, and it costs a lot of money. So we're going to use that and try to combine these. But really, the other thing that's making these attractive to a lot of buyers is you can kind of look at this as you put PV with storage. It's a near firm renewable that's more of a direct replacement conceptually for a lot of the characteristics of a natural gas plant, right? So that's good, but there's a lot of longer term things that we're trying to work on in this paper. This is really dealing with long-term complexity and risk and how you're mitigating that. The plasticity really allows you, if the system changes, if the value of different services change, if the market is completely different, these things are plastic enough. You can reprogram, you can modify them behind the point of interconnection more easily. You can add new technologies to always make your system be in the money. And you're doing that so you don't end up as a stranded investment, right? There's a big risk. I mean, nobody's going to build a coal plant now because, you already can't get it financed or insured because of this risk. There's some concern even about new gas, right? So I just claim that this sort of approach is your insurance against stranded investments. I talked about some of the other things, but it contributes, I think, to better financing, more innovation. And really the whole thing for me is about let us continue to innovate and to evolve and see if we can't come up with better ways of doing this that will extend to lots of other types of resources, including aggregated DERs. So with that, I'll just point out, I'll leave this first one actually to Derek, but just wanted to point out that I see lots of overlap with many of the other activities going on at ESIG and elsewhere. In ESIG alone, we're dealing with a great task force right now in system flexibility in our system ops and market design working group. Redefining resource adequacy is something that Derek has been leading a lot of fabulous work on and continuing the system planning working group. The DER working group is looking at this aggregated DER participation type issue right now in a big way. And reliability working group is looking at grid forming inverters, and there's lots of other things going on, and a lot of it on the global basis as well, with the Global Power System Transformation Consortium that feeds directly in here as well. So with that, I look forward to the discussion, and thank you very much.
All right, and thank you, Mark. Always great insight coming from you. So really appreciate your time today. I think the quote I heard that sums up this whole panel the best from Mark's presentation he just gave was, "Give me enough energy, storage, electronics, and software, and we can give you whatever you want." I think that was a really good way to sum it up. I think the other thing that Mark stated, which I really latched onto, was we can give you what you want today, and we can give you something different 10 years from now. The ability, the flexibility of the software to update the offerings or the services it can provide is really helpful and really a benefit of hybrids. So that flexibility is certainly something that will keep us busy for a while. And Ryan, yep, there we go. So as Mark just stated, there's a lot of opportunity with ESIG to delve into the hybrids further. And so before I hand it over to the panel presentation or the panel discussion, I did want to highlight an initiative that ESIG is now kicking off. So part of the HyFlex task force, there's going to be a hybrids and emerging flexible resource task force kicking off to really evaluate what the state of the art is for hybrids and how we can look at hybrid resources from plant interconnection, market rules, operation, and reliability perspective. So myself, along with Michael Gogging from Grid Strategies and Eric Ela from EPRI, are going to be leading a group of industry stakeholders like yourself to really come up with what's ultimately will be a deliverable of a series of white papers and more digestible fact sheets to look at what are the opportunities and challenges for hybrids. We're going to break that into 4 sections, really defining what a hybrid is, then looking at the transmission interconnection issues, as well as power flow modeling of hybrids. So what does it take to get these interconnected? What makes that unique? Then we'll look at market rules and operations for hybrids and how those may need to evolve or what opportunities there could be there. And we'll wrap it up with the resource adequacy and capacity accreditation of hybrids. And again, the way we're going to do this is really convene a group of industry stakeholders for 4 special sessions, looking at about 2 hours each, where we can discuss these topics, take notes, and ultimately use that and the input that we get from the stakeholders to come up with a standalone white paper. So we're targeting the first week of May or the second week of May there for the first session. If you are interested in participating, again, we're looking to really pull together a consortium of industry leaders, developers, grid operators, utilities, researchers, OEMs to participate. We want to hear what your thoughts are on hybrids and what you see as barriers to getting more of these systems on the grid. So again, please reach out, visit the ESIG website for more information on that, and we'll get back to you soon with more information on that task force. So really looking forward to kicking that off here today. And with that, Ryan, can I ask the panelists to pop on their video and we can pull this up and really transition over to really an open discussion, free-form discussion on the topics we've been talking about, and hopefully get to a lot of the Slido. So if you haven't done so already, please go over to the Slido page, submit your questions, or vote on the ones that you find most interesting, and we'll try to get to all of those. And so I think, there's a healthy dose of skepticism coming in through the Slido page as well. I think just, what the difference really between, or the advantages of standalone solar and storage versus the hybrid configuration. I think Mark really hit home a lot of the answer to that, but I wanted to maybe address that first and give everybody an opportunity to discuss it a little bit more open-ended. So I guess we'll start with Mark Rothleder. The ISO has certainly a lot of energy, a lot of storage, and a lot of software. And, can you talk to the perspective of optimizing an entire system versus the developers or the plant owners bringing their own device to do that? And can you talk about maybe the pros and cons to each of those and what your perspective is really as the guy in charge of making sure the market holds together? So yeah, I'll pass that over to you.
So yeah, we've been having this internal debate. Some people view the opportunity of seeing a hybrid resource as just a a dispatchable resource. They don't have to worry about the components, and you just get whatever energy or services you want out of it. That's very attractive to the operators. At the same time, there's others that view, well, having it as a individual resource and treating them as separate resources, the variable resources and storage separately, it allows us to manage that storage for grid purposes, and some people view that as attractive. So there is kind of a different view out there. If you talk to our forecasters, they'll say, well, they want to be able to still forecasting the individual resources, the VER resources separately, so that they can accurately account for them. Whereas if it's a hybrid resource, you probably lose that ability to forecast what the resource, because it becomes a dispatchable resource. Just from a interconnection perspective, I do think the hybrid or co-locate resources is a very useful and timely feature, because using the existing sites and being able to do that and develop these very quickly is actually helping us meet the needs of the near-term capacity needs. And I think that is one of the big advantages, at least in the near term, regardless of whether how you feel you can control them or utilize them. I do think in the long run that having these be more like the hybrid resource, where you just get energy, dispatchable services and energy, that does seem pretty attractive to me, and I think ultimately the operators would view that as a nice feature.
Thank you. And Andrew, maybe you want to provide your perspective on that?
I think I agree with a lot of those points, and see a lot of benefits of doing that. I guess the one thing I would just sort of raise as an additional point is just trying to, as you start to get to that place where the system operator is basically just managing these bids that are coming in and sort of making sure that they're meeting all of the system needs, and potentially starting to lose visibility as to exactly what is the resource that's behind that, and what's it doing, and what's the forecast for that, or what's the state of charge, and those various things, is that there's some trust that has to kind of come along with that. And that trust should build in part on experience, but then also sort of a clear understanding of the allocation of risks with that. So under those circumstances where the system suddenly becomes very tight and you need a lot of those resources and you're counting on them to do something, you have to make sure that if that asset isn't providing visibility to you or something like that, but they're saying, here's where we plan to be with that they have sort of fully sort of incorporated into their their strategies or whatever, the full risks of them not showing up with that. And I think that just sort of like growing the comfort level that those assets are going to do as they're saying, irrespective of your ability to see what's behind it, I think is going to be sort of one of those important stages and milestones in growing the comfort with hybrids.
Well, it might not surprise you that I would disagree a bit here. I think actually that, first of all, I think there's a huge difference. There's not just a market participation model issue. There's a whole philosophical and real difference between hybrid and co-located that I think I've tried to point out. It's not just a participation model. But I don't, really what I'm saying here is I'm saying it's time for renewables and all market participants to grow up and act like other generators. And I'm not talking about withholding any visibility. I'm not talking about withholding any forecast of the technologies within it. I just say that they ought to be treated the same as you treat a conventional plant. Say that was a gas plant. You want a forecast about, okay, how much gas did you buy today? How much gas do we have hour for hour through the day? Yeah, that's the same as giving you the PV forecast piece of that as well. This is the energy forecast that I have for the day. All I'm saying is that you shouldn't use that telemetry and that visibility to restrict my offers, because I'm going to completely control, what I'll offer you, everything I can do. The market should co-optimize that to come up with the highest and best use of everything I could do for you, right? So all I'm saying is everybody had to grow up. We had to treat all resources the same. And that does mean that if you're going to participate as a hybrid, you have to become much more sophisticated and actually take responsibility for satisfying the offers that you make that are cleared by the market and be penalized on a performance basis for that, as would any conventional resource, right? But I think that this is really just trying to raise everything to a higher level and say all market participants should grow up and be responsible for what they offer to the system. And the market should worry more about co-optimization and clearing of that and hold people accountable. Now it's tricky. You have to be more sophisticated. Also, it's not, it doesn't matter, the AC or DC on the reliability. For interconnection, you're still going to go through an interconnection study of the actual properties, electrical properties at point of interconnection. So if you change an inverter, yeah, you're going to have to probably restudy that, right? If you don't change an inverter, it doesn't change the dynamics or the frequency response or anything behind there, so you ought to be able to innovate more freely in that case. But I don't see that there's any conceptual difference here other than saying that these renewables that are now hybrids should be treated more like conventional resources. What's wrong with that?
Yeah, thanks, Mark. I think it's obviously a pretty strong shift in the way we've thought about wind and solar. And so I think you're right. It's probably about time. I think another perspective that I brought to kind of grappling with this is should it be a standalone system resource or a hybrid for a developer? And fundamentally, at the most basic level, the way I've tried to summarize this is, in a deregulated market, we rely on merchant generators to come forward and provide power, and it's really up to them, and they have profit maximizing objectives, and they want to not only provide electricity and grid services into the market, which is obviously to the benefit of the consumer, but they have an obligation to protect their asset, to get the most out of their asset. And so I think, to me, if we're going to have a deregulated market, an open market, we have to give the plant owners and the developers the tools that they can run their plant the way they want to run their plant. And so I think that's kind of the perspective that I brought.
If there's a market service and you're giving me a price that tells me what market services are most valuable to you at any instant, you would be surprised how creative and innovative and how much I'm willing to invest in order to pursue those price breaks and to be there for you.
Yeah.
So don't underestimate that as well.
I agree. I agree with what's being said, but I think this is we're just coming to scale and getting our arms around these things, and we're still in the process of evolving the markets and the products to really acknowledge that and do that. So while I think if I was looking out 5-10 years, I would agree that we will get there, but I don't want to get there prematurely and then have a bad outcome that then takes us in a bad direction overall. And we're seeing that this summer. We are going to have to take some control over the storage resources, especially in the evening hours on the hottest days, because we have to make sure that they're charged and they're ready to go for that evening peak. Is that where we're going to be in another 3 or 4 years? Probably not, but that's how we're going to have to manage them for this year as we transition to the scale that we are.
I agree, and I'm good with it. Yeah, you're absolutely right.
So that brings up another question that's coming through the Slido that I wanted to touch on. Maybe again, Mark Rothleder, you can kick this off, but and it kind of goes to the comment you just had. So if a hybrid plant is going to deliver the services that they want to deliver when they want to deliver it, how does in the way they want to deliver it, how does the system operator enforce that reliability? So from the CAISO perspective, if you're getting all different flavors of technologies and plants, how do you go about making sure that the services you're asking for, you're getting the correct ones back? So I'll start with.
Well, I think the answer is in the question, because I don't think it's just a matter of what the resource wants to provide when they want to provide it. I think it's this dance between the market sending the right signals for the right stuff at the right time and then the facilities able to provide that service and responding to those signals. If you get those signals right and those signals represent what the system needs, you're in that sweet spot of having the resources do what you want them to do. If you don't have the products all in place, sufficiently developed, then you fall back into operator actions, which is not ideal, but as a transitional mechanism may be necessary. So I think this is where we're going to learn, create new products, additional products, and send the signals that are necessary for these resources that are flexible to provide what is needed by the system at the right time, because they're being compensated and they're seeing the signals for it, not just because they want to do it at whatever time they want to do it.
Right.
All right. So moving on to the next question. I think one I had, and I think all three of you could provide a good perspective on this, is just what do you think the largest barrier, either market, interconnection, or regulatory, a barrier that you're seeing today out there in the market that is holding back hybrids from being a larger component of the system? I guess, Andrew, you want to start with that one?
Yeah, I think that from what we've seen, that there's been this shift in the technology costs and so on that have come down and sort of allowed these to be introduced. And I think that we're seeing sort of a rapid uptake of them. So I think that getting the costs into the right place it is going to basically now make that sort of more of an economically attractive option. And now we're starting to see a lot of people starting to get into the interconnection queues and start to move those forward. So I sort of see this as a rapidly changing wave that's coming. And I wouldn't necessarily say that there's obvious barriers to continuing to do that. It just seems like it's starting to unfold. I would note just those things about, there's going to be some, trying to sort out what are those right participation models and how do we sort of ensure that we've defined our products correctly and things like that are those things that need to be worked out. But it seems like that's going to be needing to happen kind of in parallel with this wave of coming technology.
And I guess we'll throw it over to Mark Ahlstrom. Putting your developer hat on for a minute, what do you see as the biggest barrier, fortunately you have somebody from the market operator to hear your gripes, but whether it's in KAISO or elsewhere, what do you think's holding us back?
You can just call me Mark if you want to.
I'll do that offline. No, my biggest gripes are not with KAISO. I think really this is just part, we're looking at the most massive grid transformation ever over the coming 10 to 15, 20 years, right? And to do that, you have to build a massive amount of resources. So the biggest problem is not even unique to hybrids. It's, if it takes 3 or 4 years and, millions of dollars to get through the interconnection queue, you're not going to be able to build this new stuff of any type in a timely or cost-effective way. So a lot of it is just our biggest problem, is really with this massive transition. And actually, I think hybrids help that because we can put more capability at each interconnect, with hybrids than we can with standalone resources. But it still is a major barrier. The other thing is material change. When do you have to go back and restudy it? And when can you go ahead and add storage to an existing wind or solar plant, right? Or take a wind plant, I want to add storage under it, and I want to add a PV under it, right? That's surprisingly difficult to do, even if you're not going to change your interconnection limit, right? Because it becomes a material change, has to go back through the queue. I think we have to question whether that can't be simplified and sped up. And there's a lot of work going on with that. It's still is a work in progress.
And Mark Rothleder, I guess, what are you hearing from, or I guess, what's the biggest challenge you're seeing as you have to evolve these market rules? What's the big sticking point?
Just time. I mean, I think there's clearly the demand for market rule change. There's a demand for these resources. I don't think that's a barrier anymore. You could say interconnection is a barrier, but I think we've done a fairly good job of trying to, at least in California, remove that barrier or be responsive to the demands and not have it be a barrier in and of itself. The technology is not a barrier. I think I think the biggest thing right now is now that we're at scale, learning from it and continuing to adapt the marketplace so that we get what we want out of these resources. And that's not a barrier. It's just a matter of the evolution. We didn't have the scale to this point.
All right, I'm going over to Slido again here, and I guess I will be remiss to ignore this is a democracy, so I got to go with the one that's gotten the most votes, and it came from Professor O'Malley. So is there just a market failure here that's saying there's a role for these hybrid resources? Or is it easier to solve this on the market side and just say, if there's a service that we need that's not coming from the resources we have today, should we just change the way we craft the services? So I guess I'll open that up. Does anybody want to touch on that? Is this a market failing or not?
I don't think it's a market failing. I guess you could say it's a market failure, but I don't think it's a market failure. I think it's a market evolution, and as things evolve, you're going to find stickier parts of the evolution than other parts. And we are moving away from services from conventional resources and seeking to get those services from the broader set of resources. And as the conventional resource fleet retires or evolves itself, the demand and the value of those services for the new fleet of resources will start to emerge. I don't think it's a market. Again, I don't think it's a market failure. I think it's the natural market evolution. And I guess sometimes we want to accelerate it because we know that the opportunity is there. But then when we start trying to force it before it's sequencing, and I think we're probably getting caught up in some of that sequencing stickiness. Again, I guess I'm not as pessimistic as saying it's a failure.
I would agree. Actually, I don't consider it a failure either. I think what Professor Malley's talking about, though, is that we're very used to production cost modeling kind of approaches here. We said, just give me all the pieces. I can do this top-down optimization and use all of them as a system optimal way. That sounds like that should be the way to get the most optimal solution, period, right? And so anytime you start aggregating it or essentially, we all are hesitant about doing that because we worry about, well, we're just creating a smaller balancing area and I'm trying to get rid of all those and aggregate it, right? Yeah, I get that. But you also have to look at, well, who's going to build this stuff? What's their risk? Will you get all those pieces? Because, you're not going to build a piece if it might be valuable today and not valuable in 5 years. Therefore, you aren't really getting the optimal resource mix. And this is, I think, is a compromise where we say that there can be optimization. This happened with the software industry too. Everybody thought, well, you're never going to want to do object-oriented programming because it's less efficient than just writing straight line Fortran, right? Well, we got past that a long time ago and realized that actually was not the case. It actually turned out to be more efficient and certainly more maintainable. I think the same sort of thing as the evolution we're going through here.
I would just add that, in the very narrow sort of short-term sense, because I agree with a lot of the points that have been raised, but I do think that sort of having an example where you could have the full ITC applied to storage if it's coupled with a solar plant or something like that, but not get that when it's not. That is a factor that has been part of this and that has to be acknowledged, and that's not really sort of driven by system needs. So there's cost savings that are happening on the construction side and this policy side that are a factor in that's one side of the coin, and then you have to look at these sort of market side. So even if there wasn't a broader system market failure, there might be things that are kind of weird on the cost side, and that'll phase out over time, and so that's going to be less of a driver going forward.
The incentives always can be distorting. I agree. The incentives are never perfect, especially when you're trying to look at the market, right? But I do think the ITC and the ITC charging is vastly overblown because we're putting in bidirectional inverters. We'd be happy to charge from the grid part of the time if that allowed us to capture the higher value services, right? You don't have to charge 100% to get the ITC. You have to charge at least 75% of the hours over the year, over the energy over the year, basically, right? And you would be prorated down, but big deal. If I can collect more revenue by charging a few percentage time, I'll do it in an instant. It's an economic choice, right? So a lot of those are not as much of a barrier as we think. Now, I agree that a standalone storage ITC would eliminate that They could be better. You know, they're never great.
Yeah.
We take what we got.
Yeah, but I mean, on the ITC question, I mean, I think this is again part of the learning. I don't even know if we really know how it's going to play out. Sometimes I hear, well, yeah, you could do some grid charging, and there's enough flexibility there. And then I hear others say, well, no, you're not going to be able to do grid charging at all, which is fairly limiting. And so I'm looking forward to this year. I'm looking forward to the next 2 years to really see how the ITC plays out. It's going to roll off eventually, so it's not going to be a long-term factor.
Yeah.
But it is going to be a short-term, I guess, distorting effect that we're going to have to work through.
But a lot of the co-located resources in your territory, though, you know, they're AC coupled. You know, they were existing PV plants, put in storage there. You're sharing the interconnection.
Yep.
I mean, the IRS rules are financial rules. You just have to kind of show that the hours where you charge the battery, you were also producing that much PV, and that's an IRS okay, right? It's not physically charging.
I'm actually looking forward to the IRS getting some test cases so we get clarity about how it's really going to be treated, because I don't know.
Yeah,
and I just want to clarify that there's sort of two elements. I think one of them that we've been talking about is the requirement on grid charging. The second element is just, you know, if I have a storage asset, I could go put it near the PV plant or the wind plant, or I could go put it in, you know, downtown urban area or something like that. And I'm not going to get the ITC if I go put it there without that solar part of it. And that's the other element, is sort of there is this, like, you know, part of the ITC that brings them together in addition to that grid charging part you're talking about.
But I agree, and I've seen some of your papers from your associates there too. But, you know, like the RIA study in MISO shows that you actually want the storage out by the generation to provide the reliability services. You don't want it by the loads. And I would also argue that if you look at just a price taker model, in the current historical sense, you're omitting the real reason why people do long-term investments in plants as hedge value. I don't want that storage sitting there or that naked PV sitting there. I'm hedged better by having that combined, right? And so people do not actually make 25-year PPAs based on purely on the spot market revenues and the capacity payment, right? There's other hedge value. That's the big reason why most projects get built, you know, so that has to be considered as well.
Yeah, and that's one of the things we've heard too, just from other developers, is like, they're doing it in part because that's what the customer is asking for, right? And I think that kind of goes along the lines of, like, it's a better hedged asset potentially than it is standalone.
Yeah, that's right.
All right. I have a list of my own questions, another list of a lot of questions that came in through the Slido, but we are running up on the end of the session here. So as Charlie said before, the panelists are all going to take a crack at answering these questions written, and we'll post those with the results of the webinar. But with that, I'd like to give my sincere thanks to Andrew, Mark, and Mark. Really appreciate your time, your perspective. Always a pleasure to speak to all of you. And with that, Charlie, I'll pass it back over to you.
Okay, I've got to get off of mute here first, Derek. So, great panel, really great discussion. I really enjoyed it and learned a lot. And I want to thank all of you for your great presentations and discussion, and all of the participants that asked the great questions that will get answered hopefully in the next few days. I think the session's really offered some great insights into the evolving hybrid power plant landscape, and I hope it's provided some stimulating food for thought for everyone. I would also like to remind you that spring workshop sessions are being held on Tuesdays and Thursdays through April 8th. So we have only 1 week left to go. We have a session next Tuesday on co-optimization techniques and practical applications, chaired by Lindsay Anderson of Cornell. There's no charge for the sessions. You're all invited to attend. Further information on registration is provided on the ESIG website at www.esig.energy. So thanks everyone for your participation. Stay safe, and we'll look forward to seeing you again on Tuesday. Bye now.